My name is Alejandra Crespo. I study electrical and mechanical engineering. My topic is about demystifying over-the-air OTA testing important antenna parameters, test system setup, and calibration. What is an antenna? An antenna transmits and receives signals over the air, therefore antennas are used to transfer guide electromagnetic waves or signals into electromagnetic waves that propagate in free space and vice versa. Generally passive antennas can both transmit and receive energy and are thus reciprocal. Therefore, all mentions on radiation and transmission are also valid for the section of radio waves. Antenna parameters. The antenna's parameters will have voltage, extended wave radio VSWR, the voltage in standing wave describes how much RF power is reflected by a low instead of being exact. The voltage standing wave radio is determined by measuring the reflection and confusion. Efficiency. The antenna radiation efficiency describes the area of power radiated from the antenna pressed to power effect by the radiation efficient only and accounts for losses in the antenna itself. Total radiated power TRP. The power radiated by the antenna is also called the total radiated power. It is defined as the radiant intensity integrated over the whole sphere around the antenna. Directive. Directive describes how directed the power of an antenna is to a certain direction. Is the area of the radiation insensitive for a given direction to the radiation intensity that would be produced if the radiated power efficient isotropic radiated power EIRP. The EIRP denotes the absolute output power in given direction. If no direction is defined, the direction of maximum radiation intensity is implied. The EIRP is the power and ideal isotropic radiation requires a spoon power the two active. The same power designed in the given direction. Radiation partner. The radiation partner represents the spatial distribution of the quantity that characteristics of the electromagnetic field generated by an antenna. For reciprocal antennas, the transmitted and received partners are identical. Polarization. Every electromagnetic wave has certain polarization, meaning the orientation of the E field in space. The polarization of an antenna is determined by the polarization is the electromagnetic wave bandwidth. The bandwidth of an antenna is known as errant antenna characteristics, but is defined as the range of usable frequency in which the antenna performs at a specific with the respect a freely defined set of parameters. Parameter flow chart. The figure shows some antenna parameters as well as power values that occur in and around an antenna. The power is measured to the transmission line by generator. It is available to the antenna. The antenna will accept some power and reflect some power depending on the machine, reduced by losses in the antenna caused by RL. The remaining and power is radiated for the antenna to generate a sense for antenna radiation intensity in different directions for the antenna aperture. I present a video about what is antenna gain.
A radio antenna is a device that takes electrical power and enables it to radiate into free space as an electromagnetic wave. Since radio waves are invisible and somewhat hard to imagine, we'll use a light bulb as our basic antenna. Now, let's assume that our light bulb takes 1 watt of electrical power and radiates 1 watt of light. We would say that this antenna has no gain, or to put a number on it, it has a gain of 0 decibels, or 0 dB for short. It's a simple bulb and it radiates equally in all directions, up, down, left, right, forwards and backwards. The technical word for this is isotropic. Our light bulb has an isotropic radiation pattern. Now imagine our light isn't bright enough for us to see. We can't turn the power up, but we do notice that a lot of the light from our bulb is going in directions that we don't need it to. We decide to bring a mirror up behind the bulb so that all the wasted light going in that direction is reflected forwards. We have effectively doubled the brightness in front of the bulb. It is now equivalent to a 2 watt bulb. We express this as 2 watts equivalent isotropic radiated power, or EIRP. We've achieved this doubling of the signal by giving our antenna some gain. We express this gain as 3 dBi. The 3 dB simply represents a factor of 2, and the I tells us that the gain is expressed by comparison to the isotropic condition. We can take this further. Bringing down another mirror to form a corner would give us yet more gain. The light is all going out into 1/4 of the sphere now, so we have an EIRP of 4 watts from our original 1 watt signal, achieved using an antenna with a gain of 6 dBi. If we need an even brighter beam of light, we could use a curved or dish-shaped mirror. This would provide a bright but narrow beam of light. So what have we learnt? We have seen that changes to an antenna do not increase its power, but we can increase its effective output power by focusing the radiated signal. In effect, gain is achieved by focusing the antenna.
And applications in electrical mechanics. We have first, separate signals for individual elements in the receiver. Second, code division multiple access. And third, baseband processing or RF connector for signal generators. Compact CRTR OTA chamber for 5G VFR2 testing.
How to combine fast measurements, high performance, and a compact design when measuring a 5G device over the air. The answer is ATS800R. It is a compact antenna test range chamber which creates far-field conditions in a very compact setup. The reflector integrated in the upper side of the chamber creates a quiet zone of 20 centimeters with the highest measurement accuracy. And with the help of the positioner, we will get the 3D data out of the TOT. In this specific test scenario, we are creating a 5G FR2 signaling connection between the mobile phone and the combination of CMX-CMW radio communication testers. This complete setup is the perfect environment when testing 5G devices. Far-field conditions in a chamber as big as a rack. This is this ATS800R.
Different antenna types. There are many different types of antennas. If tailored to a specific use case, designing and about the antenna is most often of compromise between optimizing for the different antenna. Parameters. Different antenna types include dipole, monopole, horn, bivalve, jagged, budge, stem, microstrip, parabolic, load period, wire guide, loop, airway, and many more. Each of these antenna type is designed for a specific purpose. antenna types
If
come
you're implementing
challenge.
a wireless network, you may need to use different kinds of antennas to accomplish this. In this video, we'll look at a number of different antenna technologies and see which one might work best for you. A very common antenna type we see when we purchase some of our wireless access points is an omnidirectional antenna. This is the antenna that simply points into the air and you get exactly the same type of coverage wherever you happen to be anywhere around that particular access point. The signal is evenly distributed on all sides. That's why we call it an omnidirectional antenna, because no matter where you happen to be, you receive the same signal strength from that antenna. In many environments, this is a pretty good choice because you can put the antenna in a central area, and no matter where you happen to be, you're getting the same signal strength from anywhere around that access point. The problem occurs when you want to have a little more signal in a particular area. An omnidirectional antenna is very good at evenly distributing that particular signal throughout. If you want a little more signal in a particular area, however, you'll need to use a different kind of antenna. In those cases, you'll want to use a directional antenna. And as the name implies, this allows you to focus the signal into a very particular area. This also allows you to increase the distance because you're taking all of that signal that normally was sent omnidirectionally and you're now focusing it all in one particular direction. This means that we'll be able to have a very focused signal in one particular direction for both sending and receiving. This means if there are other signals that are off to the side that are not in that direction, we're not able to send or receive to them very well. This directional antenna is really focusing all of that signal to one particular place. The performance of an antenna is measured in decibels. This relative measurement means that if we're able to use an antenna to effectively double the gain out of a particular antenna, that means it increases by 3 decibels. And you can compare the decibel ratings of different antennas to get a feel for how that antenna might work for you. One type of directional antenna is the Yagi antenna. This provides us with a way to really focus our signal in one particular direction, and because of that, we get a very high gain from a Yagi antenna. Another type of antenna is the parabolic antenna, where it can receive a lot of signals down a very wide area on this curved back of the antenna. This curved back means that as the signals hit, they're going to reflect off of that into a single point that is reflected right into the point of that antenna. So as we're receiving from many different areas, we're able to instead focus those signals down and receive much better for that antenna.
System calibration is that a network analyzer can straightforwardly measure the secondary parameters of the use cases: frequency, response, information, and reflection coefficient of the cable. Measurement of a dot will feature a clean and well-defined signal at the dot. For calibration, multi-signal generators and signal of the spectrum analyzers can use these current parameters of a test setup to move the calibration plane under pressure. Their measurements similar to the bird calibration of a network analyzer. Depending on the test equipment capabilities, the instrument may be able to compensate for frequency response in an amplitude and phase action, taking reflections into account. OTA RF performance testing for 5G.
The first RF test cases have been defined within the 3GPP 5G NR standards. Rodosbus actively follows the 3GPP standards, and this year we are presenting the new pre-5G NR OTA system. The system is a combination of the world-leading TS8980 conformance test system and the new antenna test chamber ATS1000. 5G antenna manufacturers, also operators, need a viable solution for research, diagnostic, debugging, and also type approval. This system provides a solution for 5G module measurements following the 3GPP standards. The system components are SMW generator, FSW spectrum analyzer, ATS1000 chamber, and measurement software contest. Let's have a closer look to these last two components. The antenna test chamber ATS-1000 is a compact and mobile chamber. It supports both far-field and near-field measurements. The high-precision conical cut positioner integrated in the ATS-1000 ensures fast and accurate 5G module measurements. In this case, for today's live measurements, we have an active duty. It is an 8x8 patch array antenna and it's radiating at 28 GHz. The system is fully automated through the measurement software contest. Measurements like TRP, EVM, ACLR, and spurious emissions are possible using the antenna test chamber ATS-1000 and the measurement software contest. In this case, we are performing TRP measurements while showing ACLR value. The 3D measurement pattern is illustrated in 3D. The new Rodon-Schwarz pre-5GNR OTA system is a fast, accurate system for performing 5G module measurements over the air.
Pros and cons. Pros versus cons. Pros. Each final test distance, there is an optional measurement antenna. FF results in a much smaller measurement environment. RF invisible material is contained in the region of controlled temperature in a small space. Equipment in the chamber untouched and decrease the efficiency for temperature change. Cons. The FF distance cannot be achieved and IFF measurement techniques are not applicable. An F measurement includes no real-time results. It's not feasible to change the temperature in the whole OTA chamber or room. It takes much more time and energy than necessary to apply temperature changes. Applied in Ecuador and conclusion. Applied in Ecuador, we have calibration data can be handled by using automation software and F measurement with a calibration method conducting light, test setup in signal generators and signal on or spectrum analyzers, and correct use of chambers and FAT, COD, PWC, or NF. Antenna radiation pattern measurements using shockline barrier network analyzer.
Good morning, my name is Ferdinand Gerhardes from Amritsu. I'm from the engineering and technology team here in EMEA. And here and today we would like to present you a novel and new way of measuring any kind of antenna in the E-band range. Why is this so important today? On the background of 5G, it is very important to have the capability to measure antennas. And to measure an antenna you have to have first a VNA, and this shockline Anritsu E-band VNA is a very novel piece of technology. We are using for any kind of frequency conversion the so-called non-linear transmission line principle, and that is the reason why these modules are so tiny and so small. And with two of these modules and two of the antennas, we are able to measure antenna pattern. What is missing is you have to have a rotating table, and on this rotating table is the antenna under test. And what we would like to do next is this antenna is start rotating and this antenna is sending a signal, and then we can see the antenna radiation pattern. So first of all, the antenna is moving into a start position, and then the antenna is moving back in equidistant azimuth points until the antenna has arrived on the other end. And this is here just a proof of concept. Usually an antenna is radiating in the azimuth as well as in the elevation, and then finally you're getting this nice looking three-dimensional antenna radiation pattern. And this is the result what engineers are looking for in order to characterize antennas for 5G applications or antennas that are not anymore separate. This means antennas that are based on the chip level. And for this kind of applications, you must have the ability to maneuver the VNA modules in a very easy way. So let me summarize. We have here a technology that is unique.
starting at 52 gigahertz going up to 92 gigahertz in a technology that's called nonlinear transmission line. And it is also possible to extend the short cables up to 10-meter cables here. And by doing this, it is possible to dislocate the antenna modules for more or less any kind of antenna measurements. Thank you very much for your attention. That was a very brief introduction into the Anritsu way of measuring E-band antennas in today's world.
And finally, we have a conclusion. These challenges are the angular resolution and the search for worst-case antenna configuration, and F to FF transformations are high acquired in the text system electrical and mechanical. Knowledge about the broad antenna and additional and post-processing steps taking care of all requires will have over just very require FF results in a much smaller measurement environment. Finally, for each finite test distance, there is an optimal measurement antenna that will provide an average accepted power that is dependent of test distance. Well, thank you very much, and over time, thanks for your attention. Bye.